All right. In a couple places in here, I don't know if you can see, there's a big sort of massive bed right here. Very, very blocky in terms of the way it's weathering. That's in contrast to like this more thinly bedded unit up here. See the contrast between those two?
Yeah.
All right. But both of them have these little crinkly layers that are running through them. You see those little crinkly layers?
Yeah.
Those are sort of poorly developed stromatolites. Aborted stromatolites, if you will. You get this sort of biofilm that's encrusting the bottom, and then it gets buried by a layer of sediment. And then a few survivors go out and they recolonize the bottom, creating this crusty little biofilm, and then they get killed by being buried. All right? So these are like little algal mats that are being preserved. They're not fully developed into nice big bulbous stromatolites, but they're the same sort of thing. You know, a layer of bacterial slime on the bottom of the ancient ocean. Yeah.
Why do you think this section, like over here, it has like sort of a stripe compared to the sides? You know?
So, well, yeah, this is more massively weathering, and for whatever reason, this one actually I think may be more silicified.
Or is that not really?
Yeah. When I'm trying to scratch this part with my key, it won't scratch it. So this part's been turned to chert. Probably this part has as well. And I can scratch that. But chert tends to grow this black stuff on the surface of it.
And isn't chert deposited in deep, deep water?
Well, if it's depositional chert, but replacement chert can occur in any sort of depositional setting. So basically, remember when we talked about sponges briefly, we mentioned that there's two kinds of sponges. Those that make their spicules out of calcite and those that make their spicules out of silica. All right? Well, if you have a whole biological community that gets buried in a limestone like this, the silica is not stable, and it dissolves away, and it's flowing along in the groundwater, and it gets reprecipitated in these little nodules called chert nodules. So they're actually concretions. Remember we looked at concretions last week in lab, these inorganic growths? So the sponges are supplying the silica that's then getting reorganized into these concretion-like growths. We'll see those a lot better at the next stop. All right, so I'll talk more about that there. There, they're extremely prominent. Here, it's kind of fuzzy.
What made you find this spot?
I was brought here by a University of Maryland sedimentology trip.
And they probably drove by it.
What's the middle plan? The fracture like almost looks like completely different.
This?
Part, right?
It's limestone. It's just massively bedded limestone. So this represents maybe a period where you've got more stable conditions over a longer term, whereas up above you've got sort of this pulsing, you know, of sediment on, off, repeatedly.
There's also
right?
calcite in it too, right?
Well, the whole outcrop is essentially calcite of one form or another. Okay, so it's mostly limestone. What's this little hole here with the red dirt coming out?
Pothole? No.
Well, the red color suggests that the dirt is oxidized.
Oh.
Not a pothole.
I don't know.
Ant farm over there, though. There's a bunch of holes. They're chomping around on it.
There's another little hole with red dirt coming out of it.
Is that just from erosion? Or just
What kind of erosion?
I don't know, one that pushes dirt out of the
Yeah, what kind of chemical erosion?
It's not Benson.
These are little caves. They're little caves. They're too small for people to crawl in. But
Isn't cave formed by calcite at groundwater where ground level crosses the ground, basically?
caves do form in calcite composed rocks. Most caves are in limestone. This is limestone. You guys may have heard that the Shenandoah Valley has these big cave systems. Like we passed signs for Skyline Caverns. And there's also Luray Caverns, right? So these are just smaller versions of those. So the caves themselves are quite young, much, much younger than the rock that they're carved in, right? So we said the Conococheague Formation is Cambrian in age. Approximately how many millions of years old is that?
540 maybe?
Okay, so the beginning of the Cambrian is 540. This is probably more in the neighborhood of 520, 510, something like that. I can't give you a precise age on it, but tough. What's that?
How did the caves form?
They form when groundwater, which is slightly acidic, dissolves away the limestone. Just like when you put acid on a calcite sample in lab, it fizzes. All right? The same thing happens naturally, just at a slower rate. As raindrops fall through the air, they pick up a little bit of carbon dioxide and makes a weak acid called carbonic acid.
That age, is that the age of the formation itself? Or the...
Yeah, so the age of the formation is somewhere in the neighborhood of 520 to 510 million years old. And I can't be more precise than that because it's a sedimentary rock and it's impossible to date sedimentary rocks directly. You have to date them when they have like volcanic ash layers in them or they're cross-cut by dikes, that kind of stuff. All right, so what does this tie into to what we've learned about in class?
The different type of sedimentary rocks are deposited in different environments.
Okay, so there's that, of course, but what specific episode does this correspond to what we've discussed in class? Transgression, okay, so basically seawater flooding up over the North American continent, all right? What's the name of that particular transgression?
Sauk.
The Sauk Sea, yeah.
It was
the
on
Sauk,
the quiz.
The Sauk transgression, right, came up basically starting in the late Neoproterozoic, continuing through the Cambrian, and then peaked out in the Ordovician, and then you had a regression, all right? So this is Sauk Sea sediment, okay, the carbonate factory that I went on and on about in that online lecture, okay? Everybody with me? Mm-hmm. Okay, good. All right, back to the vans.